All right. Can everyone hear me? Okay, so I'm going to be talking about some joint work with Alex, Jen, and Stephen. And so I'll get right into it. So we're going to be talking about the contextual bandits framework. And basically what I'm going to do is detail some issues that come up with externalities in the setting, and then talk about some assumptions and some algorithms that can actually deal with those issues. So the contextual bandits setting is kind of generally as follows. At each time a user shows up with some feature vector, we have to make some decision, say in this instance a movie to recommend to them. And so we make some recommendation and observe some reward. Okay? And we're going to measure our performance in general in regret, which is pretty standard in this literature. And that's simply the difference between the accumulated reward that we got over time compared to the optimal policy, what the reward of the optimal policy would have been. Okay? And so I mentioned that I'm going to be looking into externalities. So what do I mean by externalities? In general, externalities refer to impacts of users on other users. Okay? And these can be positive or negative. In the online learning setting, there's a couple sources of externalities that this user faces. One of them is the data that we've gained from past users, right? If we haven't gained a lot of data from past users, then we actually can't make a very good decision for this current user. But one thing that's kind of unique to the online learning setting is that there's also an externality that arises from exploration for the sake of future users. And what I mean by that is, in most of these settings, if we were to just ignore all future users and do what seems optimal for this current user, we actually would not collect enough data to perform well in the future. And so I'll be talking about how we can kind of mitigate these things and give some examples of where externalities can arise. The first thing I want to do, though, is rule out something that maybe a lot of us have seen as examples of externalities that people impose on each other. And that's this kind of common thing that you see in supervised learning where you have kind of heterogeneous groups, and there's one policy that's good for one group, there's a different policy that's good for another group, and there's really no way to reconcile them. And we're actually going to assume that this is not the case. Okay, we want to focus only on the externalities that arise due to learning. And so I'm actually going to be assuming that we're in a setting where there's one single optimal policy that is optimal for all users. Okay? I'm going to be dealing with settings where there's different groups of users, and I want to just make the assumption up front that there's one policy that's optimal for all of these groups simultaneously. Okay? So then how can there still be kind of negative externalities at this group level? So I'm going to present an example to you. I'm going to do this informally. I don't really have time to treat it particularly formally, but this should hopefully give some intuition. And the basic intuition that I'm going to give you is that adding data from a different subpopulation can actually harm a subpopulation. So let's say I take this instance, and my online learning setting is that I'm giving people driving directions. And there's these two bridges that I can choose to route them across. And I don't know the travel times across these bridges. And for now, I'm going to assume that all other edges have 0 travel time. Okay, so I'm routing users, I'm learning about these hidden parameters, theta 1 and theta 2, which are just the travel times on these two edges. And the key thing to point out here is that the standard algorithms in this literature, UCB or upper confidence bound style algorithms, favor routes with more uncertainty. So all else equal, they'll tend to favor the edges, or favor routes that have been taken less frequently. Okay, and so for this example, I'm going to set theta 1 is smaller than theta 2, so if you look at this graph, if you're going from A to D, there's only one option. You can only go through the top bridge. Similarly, from C to D, there's only one option. And the only choice that we're ever going to have to make is when a user shows up and wants to go from B to D, I can either take them through the top bridge, which I don't know this, but it's actually the better one, or I can take them through the bottom bridge. Okay, so let's say I have some minority group or some smaller group, which has two types of users. Some need to go from C to D, some need to go from B to D. Okay? Now, in this example, as I said, the ones who need to go from C to D can only take this one path. And therefore, because there's more uncertainty about the top edge, the ones that need to go from B to D will get routed through the top edge. Okay? And so actually, we're pretty much optimal in this case, because everyone who can take the top bridge is getting the top bridge, everyone else is going through the bottom bridge. Now, what happens if I add in this larger majority population that's all going from A to D? Okay? As we said, there's only one way to get from A to D, and that's using the top bridge. And so as a result, for my minority users who are going from B to D, which bridge are they going to take? Well, there's more uncertainty about the bottom edge, and at least when we're first learning things and we don't have a lot of information, they're going to be taking the bottom edge instead. Okay? And so I haven't treated this formally at all, but basically what we can show is that in the first case where it's only the minority on its own, there's something like logarithmic regret that they get. In the second case, it's like root t regret. Okay? So I'm going to come back to this example, but now I'm going to be kind of switching gears into externalities at the individual level, and I'll tell you about how the greedy algorithm can kind of solve all of our problems. Okay? And so what is the greedy algorithm? Well, I mentioned earlier that explicit exploration harms the current user in expectation, right? It's sacrificing some utility now in order to make utility gains in the future. Now you might say, okay, why don't we just use this greedy algorithm, which just says, do the thing that seems optimal at this current moment. And this has a lot of advantages. It's consistent with users' incentives, and it's easy to implement, but it also has terrible performance in the worst case. You may just almost never take the optimal action. Okay? So why would we actually consider doing this? Well, there's been work recently about smooth analysis for this greedy algorithm, which basically says if you assume that my inputs are coming from some smooth distribution, then actually regret is not so bad. And we're going to be looking specifically at a setting where rewards are linearly related to the incoming feature vectors that we see. Okay? And so recent work has shown that greedy gets like root t regret, which is comparable to other algorithms in a non-smooth setting. We're going to make some slightly stronger assumptions. We're going to work in a Bayesian setting where we have a prior on theta, and just for some kind of ease of independence, I'm going to assume that there's batched updates to this algorithm. Don't worry about it, it's not too important. But the main result is this. Greedy is near optimal in this smooth setting. And when I say near optimal, what I mean is pick your favorite algorithm A, and greedy's algorithm matches its regret on every instance up to log factors. Okay, and this not only holds for the entire population, it actually holds for each subpopulation. And what this means is this actually solves our problem of group externalities because it matches both the algorithm that treats the minority on its own and the algorithm that treats the entire population together simultaneously. Okay, and therefore it can't suffer externalities more than a log factor. The other result that we have is that the standard lin UCB algorithm in this setting actually gets t to the 1/3 regret in this setting instead of the root t that it normally has. And so therefore the greedy algorithm also achieves this same regret bound of t to the 1/3. Okay, and I mentioned that we were in a Bayesian setting. It turns out that the prior on theta is actually, or on your hidden vectors, are actually not that important, and you don't actually need knowledge of the prior in order to get this performance. So both the Bayesian and frequentist greedy algorithms get this, this improved regret bound. The basic intuition I'd like to give you for the proof is as follows. If I can convince you, which I'm not going to do now, but if I could convince you that the greedy algorithm accumulates information in this smooth setting at a comparable rate to any other algorithm, and I can convince you that for a fixed level of information, the greedy algorithm is at least as good as any other algorithm, then I can relate the greedy algorithm's performance at time t to your favorite algorithm's performance at time t prime and make some sort of comparison between them. And so the way the proof is going to be structured is something like, at the bottom I have greedy takes a logarithmic number of rounds to collect as much information as your algorithm does in one round. And if it ever has more information than your algorithm, it's instantaneously better. And therefore, my greedy algorithm's regret at time t is like A's regret at time t over y. Okay? So I lose something like a factor of y, but I said y is a log factor, or basically a constant. And so I've matched the regret of A. Okay. And just to wrap up, there's a lot of questions you could think about coming out of this. I gave you this example of how group externalities could arise. Now, one thing you might wonder is, do these things actually happen in practice? And that's something we actually really have no idea. There's a lot of assumptions that could be reduced or removed. It would be nice to be able to remove the need for a Bayesian setting altogether. And then another thing you might want to do is improve over this lin UCB smooth regret bound, because we got t to the 1/3. It's not known to be tight, and so we suspect there's some room for improvement there. All right, thank you.
Questions?
Yeah, so I mentioned that we don't actually need to use the prior, but we're measuring regret in expectation over this prior. And it turns out that that's actually important, or for our analysis it is.
Okay, let's thank the speaker.